Did you try to look at this null state and so on?
Yeah.
Yeah, it works out.
It works.
Good, good, excellent. Yeah, this null state plays an important role in many places. Okay, I mean, yeah. It appears in the two-dimensional conformal field theories, you know, or in gauge theories. There are null states which you have to remove by gauge fixing, things like that. So they play an important role in general. But here it's in a very simple context. It's just finite dimensional spaces. No, there it's infinite dimensional spaces. Okay. So,
what is the meaning of finding two singlets?
Sorry, repeat that again.
You can find two singlets.
Two singlets.
Yeah, in certain product. Is that possible?
Do you have an example?
No. But I was wondering if possible, what's the meaning for physics?
I don't know. I mean, I don't have any example. Two singlets. Well, if there are two singlets, then there are two invariants, right? You can write down two possible invariants.
But physically, particles would manifest as two different kind of, disjoint kind of particles.
No, I don't. I mean, no, given the tensor product representations, you can have various things which come inside, right? Now, suppose you have two singlets or even n singlets in some products. No? Then you will have many possible action terms you can write down. That's about it. In fact, if you have several tensor products or several guys, not just two, then in principle you could have more singlets. Yeah. That's certainly true. Yeah. But that just means you have more freedom. You have many possible terms you can write down in the actions, which will be invariant. All right. So now we'll start going towards more kind of formal discussion of the Lie algebras. So, yeah, chapter 9. Chapter 9 is just one page or 1.5 pages. So it's just one definition there, basically. So the first step is, I mean, we studied SU2 and SU3. SU2 and SU3 we studied. But, and you already know the definitions of the Lie algebra, but this is just formalized, that definition. In definition 9.1, it is just formalized the whole thing. I lettered it down. Yeah. Okay. So I don't need to repeat that, right? I mean, this we have done many times. Okay, so the main so that's the definition of the algebra, more formal definition, which we have already seen many times. Okay. Now, the sub-algebra, also we have seen the definition of that. So if suppose some G is my originally algebra G, and there is some sub-algebra which is, let's call it H. So it is contained in G. So first of all, it's contained in G, which means that as a vector space, so G has some vector space, H as a vector space is contained inside G. And then you use, so suppose let's suppose you have X belongs to H. H. Then the X and Y, let's say X and Y. Then of course, if I take the commutator XY, since if XY belongs to H, obviously XY belongs to G, right? So certainly we know that XY belongs to G. This is in general true, right? Because G is a Lie algebra, so the commutator belongs to G. But if H is subalgebra, then that means it should actually be contained in H itself. So basically it's a subset of G, but this itself is an algebra. That's what it means, right? Algebra means the commutator closes within H. Is that clear? So for example, what we saw, I mean SU3, if you take SU3 and we had this roots alpha 1, alpha 2 and alpha 3 and plus minus alpha 1 plus minus alpha 2 alpha 3. So we have these roots, and the Cartan generator is H1 and H2. So I could choose, as we saw many times, if I just choose x plus minus alpha 1 and H1, that forms a subalgebra, right? That generates an SU2 subalgebra. Right? Because so an arbitrary element here would be, say, A x of alpha 1 plus B x minus alpha 1 plus C H1. So this will be an arbitrary element of this SU2 subalgebra. And if you look at the commutation relations between any two such elements, it is within the same set. Right? So this is an example of that. So that's subalgebra. Again, these notions you already have seen many times. The new concept is what is called ideal. Ideal, or also in some mathematics literature, it is also called invariant. Invariant subalgebra. They are the same. There's just some people prefer to use this terminology. Some people prefer to use that, but it's the same thing. So H, which is a subalgebra, H is a subalgebra of G, but such that for all xy belonging to H, commutator xy also belongs to H. You see, this is a much stronger condition, right? Because here, so for all x belonging to H and for all y belonging to G, xy belongs to H. That's the statement. So you see that if x belongs to H, certainly x belongs to G. Okay? So commutator of xy certainly will belong to G. But here the stronger statement is that it actually belongs to H. So this is the stronger. Is that clear? You see, not all subalgebras are invariant subalgebras or ideals. Because here the condition is that x, y belongs to H only if x and y belong to H. Right? But here we are saying a bit more than that. We are saying, okay, x, let's take x to be in H, but y is any element of G. Huh? Still the commutator of these two is in H. So it's a much stronger requirement. So not every subalgebra is an ideal, but every ideal is a subalgebra. Stronger condition.
One simple example would be that if we take G to be the Poincare group and H to be the translation.
Good. That's a good example. Yeah, that's a good example. Right. So let's just take some examples. So let's say first of all, you want to take a simpler example. Say U2 or UN. Right. So in UN, so let me take U2 to be precise. Then clearly generalization will be immediate. So U2, U2 is what? U2 is Lie algebra. I'm talking about the Lie algebra. Is just 2 cross 2 Hermitian matrices, right? Hermitian or anti-Hermitian, that depends on whether you put an I or not. Right? Like in the poly matrices, you can put an I there, it becomes anti-Hermitian, right?
You're talking about generators, right?
Sorry?
You're talking about generators.
Generators. Generators. So these are Lie algebra. I'm talking about the Lie algebra. So it's 2 cross 2 Hermitian matrices. But it does not have to be traceless, right? In fact, it's just any 2 by 2 Hermitian matrices. When you have an SU2, then it becomes, you have another condition, which is traceless, right? Traceless Hermitian. But now you have also the trace need not be 0. So what are the generators of this? Of course, this is true. This is the dimension of this is, in general, for UN, dimension is n squared. So for U2, dimension is 4. So we should find a basis, right? So the basis is sigma matrices, sigma 1, sigma 2, sigma 3. These are all Hermitian, but these are traceless. But to this I can add also the identity, the 2 by 2 identity matrix. Right? So that this generates a 4. These are the 4 bases elements, and any element of the U2 Lie algebra can be expressed as linear combination. Okay. But now you see, there's a subalgebra, so this is my G. G is generated by that. Is generated by this basis. By this basis here. Okay. Now let's take an H, which is simply the identity element, or any number times identity element, A times identity element. Okay. This is a one-dimensional subalgebra. It is subalgebra clearly because this is contained there, and the commutator of this with itself is 0. So in particular, it belongs to H. Okay. So this is subalgebra. But this is also, is a subalgebra. Okay. But it is also ideal. H is also ideal, is an invariant subalgebra, is an ideal. Right? Why? Because if I take the commutator of this with any element of G, you get back again, in fact, 0, right? Everything is 0. So you take the identity element and take the commutation of this with any x belonging to U2. That's 0, because identity commutes with it. So it is trivially, it's a trivially invariant subalgebra. Okay. This is not the case. If I take, for example, I can choose another subalgebra, which is just generated by sigma 3. You see, that's another subalgebra. Let's call it H prime, which is generated by simply A times sigma 3 for all A. For all A. Okay, this is a subalgebra, right? Sigma 3 with sigma 3 obviously is 0, therefore commutator is 0. However, this is not invariant, because if I take the commutator of this with an arbitrary element here, it is not 0, right? For example, if I take the commutator of sigma 1 with sigma 3, I get sigma 2, which is not inside H. It's in G, of course, but not in H. So invariant subalgebra is a very strong condition. Most of the subalgebras will not be invariant subalgebras. Some very, very special subalgebras will be invariant subalgebra or ideals. The Poincare is a more interesting example, because you see, this is a kind of a trivial example, because somehow this algebra kind of splits into direct sum of two algebras, right? You can write this U2 algebra as a direct sum of SU2 plus U1, right? That is, it's a direct sum. These guys do this commutes with that element, right? So because identity commutes with all of them. So it's a kind of trivial example. A more non-trivial example is the Poincare algebra, or even Euclidean algebra in general. For example, if I take the Euclidean group and therefore its algebra in 2 dimension, let's say, in 2 dimension. So what I have a plane. Then I have a Euclidean means rotation and translation. Okay, rotation together with the translation. So there is a rotation element. You can rotate by an angle theta, and the translation. So rotation and translations. This generates this Euclidean algebra. So rotation will be in the 2 dimension. It's a very simple thing. It is just rotation by an angle theta, right? So in particular, if I write down the infinitesimal generators, it's going to be basically 0, 1, minus 1. So, okay. This is just what this is general rotation is cos theta, sine theta, minus sine theta, cos theta. That's a rotation in a 2 plane. But then when you take the infinitesimal, you take theta to be infinitesimal, then you just get that, right? So this is the generator coming from that. So on the x and y, you have this x and y are the 2 coordinates here. This one acts as 0, 1, minus 1, 0. And the translation, this is the rotation, and the translation takes xy to xy, x plus a, y plus b. So, but now you see, so the full algebra is three-dimensional. The rotation is just one in this case, and the translations are two translations. It's three-dimensional. Now the translation algebra, translation part of the algebra is a subalgebra of this, right? Because if you take two translations, you're again going to get back the translations. Okay? Actually, it's a trivial, it's a abelian algebra. So they commute. It's an abelian. The translation gives you an abelian subalgebra. Subalgebra. Okay. But now, question is it an ideal or not? That's what we're asking. And it's an ideal because, of course, if I take the translation, commutator of translation with translation, sorry, there's not trace, and there's a short form for the translation. Translation. This is 0, right? But rotation with translation is also translation. I mean, you know this structure. And rotation with rotation in this case, in this particular case, it is trivial because it's abelian. But in a higher dimension, if you have gone more than 2 dimension, say 3 dimension and so on, rotation with rotation will in general be rotation, right? In this case, it is 0. In this particular example, it is 0, but otherwise it will be a rotation, right? So this is the general structure. Poincare is exactly the same. In Poincare, you have a Lorentz transformations, right? Lorentz rotations are like Lorentz transformations are like rotation, and translation is a standard translation. So there again, you have this algebra. Translation with translation is 0. Lorentz transformation with the translations is again translations. Okay, and Lorentz with Lorentz is Lorentz, right? So you see, in these cases, I mean, whether you talk about Euclidean algebra or Lorentz algebra, Poincare algebra, you see that the translation forms a subalgebra which is an ideal. Okay. Yeah.
Why the composite rotation of the translation using translation?
Yeah. Okay. That one can see, right? I mean, like what you have seen in the Poincare. In Poincare algebra, you have seen that, right? You have not seen. Okay, so the way to understand this is the following. So what we are trying to do is, okay, let's do the finite group. That's easier to see. In the finite, I mean not just infinitesimal level, but finite transformations. So let's say I take xy and make a translation. Okay. Then I will get x plus a, y plus b. Okay. Now I do a rotation. So I rotate this whole thing now, right? So it's going to be whatever cos theta, sin theta, minus sin theta, cos theta, acting on x plus a, y plus b. Right. Now let's first do the rotation and then the translation. Other way around, opposite direction. So first I do the rotation. So I will get here cos theta, sin theta, minus sin theta, cos theta, acting on xy. And then whatever I get, so this is my x prime and y prime. Then I do the translation. So now I'm going to get this guy, which is this matrix xy plus ab. This matrix is not acting there, you see. So if I now look at the difference between these two, so I mean this I can rewrite this into, expand it, open it up. So this is the same as this matrix times xy plus this matrix, again the same matrix, times ab. Okay. So you see the rotation part is the same. Either if you come this way or that way, the rotation part is the same. Okay, but the translation part has changed. See, this way of coming in here, you get a translation, but translation of the, after rotating this original vector AB, right? But here I'm just getting the AB. And when you take the now go to the infinitesimal version and take the commutator, right? Then you find exactly the difference between this and that will be simply the, again a translation, this is all a translation, but it's a rotation acting on this translation. So that's why the rotation, the commutator of rotation with the translation is a translation. Or more generally, Lorentz transformations here with the translation will give you again a translation. I mean, you might, I don't know if how far you have arrived in relativistic quantum mechanics, relativistic RQM, because what happens is the generator of translations are nothing else but the momentum, right? P mu are the generators of the Lorentz transformation, of the translations. And the Lorentz transformations are L mu, I don't know how you, the notations you use, I don't know, L mu nu, say Lorentz transformations, right? And the commutator of these two will be simply the Lorentz transformation of this, some P prime, right? The P prime mu is simply the Lorentz transformation acting on the P.
Two terms.
Yeah, so, yeah, two terms are there. So it will be delta eta mu nu, eta mu, sorry, this is some lambda, let's say, eta mu lambda, P nu minus eta mu lambda. There's the infinitesimal version of the Lorentz transformation of P, right? Just like here, I mean, if you look at the infinitesimal version of this term, this is cosine theta, sine theta, minus sine theta, cosine theta. Then you see at the infinitesimal level, you just have 1 minus 1. So that is, so you get here A is also infinitesimal, A minus B, that structure. I mean, here it is in this case, in this analog, in this picture, this mu nu is just go from 1 and 2, because here we have just 2 dimensions. So rotation element is just R12. This is just the rotation in the 1-2 plane, right? And then you have the P1 as a P mu. This will be delta mu1 P2 minus delta mu2 P1 P1. And that's the relative sign, which is exactly coming from there, plus 1 and minus 1. Yeah, this is a somewhat more non-trivial example than compared to that, because here it just becomes direct sum, right? Here it's not a direct sum because of the non-trivial commutation relations. Here is a more non-trivial example. But in any case, so there are this invariant. This is the definition of invariant subalgebra, right? This will play an important role, although I don't think we'll talk too much about it. But this is this basically kind of because at one point, not immediately, at one point we are going to talk about the simple algebras and semi-simple algebras and so on. There, the definition of semi-simple algebra, etc., it comes through the ideal, through the notion of one uses this concept of ideal. So for the moment, it is a definition. We'll come back to it later. So this chapter is just 1.5 pages. That's why, because it has only this definition, nothing else, and there are no exercises also. Okay, now let me just quickly go through chapter 10. Chapter 10 I'll go quickly because I mean you have again seen everything essentially, almost everything you have seen. So I'll just go very quickly and then go on to the chapter 11. Okay, so these are the matrix groups and the early algebras. Groups and the early algebras. So the first example, is, let's take the general linear transformations. Okay. So I have some, let's say, n-dimensional vector space, n-dimensional vector space, and I consider the most general linear transformation. So a linear transformation can always be written as a matrices, right? Because you can just multiply by n matrix to any vector, say x1 up to xn, right? Take any n by n matrix and multiply, that's going to give me a transformation, right? But this matrix, for it to be invertible, it has to be invertible, right? Otherwise I cannot, suppose this is x1 prime up to xn prime, right? So if I choose my original coordinates and I make a coordinate transformation, linear coordinate transformation, I will get that, right? But then I should be able to invert back also, right? Okay. So in other words, I should be able to, given this, I would like to find out also this original. So it's a change of basis, let's say. It's a general change of basis, completely with no condition. You have a basis for the n-dimensional vector space. I choose a new basis for the vector space, but then this better be invertible, right? I should be able to go back into the old basis. So that condition basically says that this matrix is invertible. In other words, its inverse exists. Its inverse exists. Then the set of such matrices, n by n matrices, which are invertible, that forms a group. Okay. That forms a group, you can just check all the axioms. Group under the matrix multiplication. Okay. So let's suppose M1 and M2 are two such matrices. Then you just define the group composition rule by simply multiplying M1 times M2, matrix multiplication. So the group composition rule is matrix multiplication. It is, so what are the, you can check, so this composition is nothing else but the ordinary matrix multiplication. So when one talks about matrix groups, one means that the composition rule is always standard matrix multiplication, not some strange rule, just a matrix multiplication is the rule. Okay, so to check all the properties, of course, since it's matrix multiplication, the associativity is automatically guaranteed, is associative. Remember, this was one of the conditions of the group, associative. Then you have, this says is closure. And then you have the identity. Identity element is simply the identity matrix. Identity n cross n identity matrix, right? In an inverse, because we said inverse exists, right? So we are not looking at arbitrary n by n matrices. We are looking at only those n by n matrices which have an inverse. So by the definition itself, inverse exists. So what does it mean to say inverse exists? It means the determinant is not zero, right? For any n by n matrix, if determinant is not zero, inverse exists, right? So this is the set of all n by n matrices whose determinant is not zero. Okay. So what is the dimension of this? The dimension of this group is clearly n squared, right? Because there is no equality condition here. There is only inequality condition.
Because you get all the entries are real numbers.
It depends on, so you can either choose real or, so at the moment I was thinking in terms of real, but you can also think in terms of some complex numbers, Z1, Z up to Zn. In that case, this would be complex. So there are two GL, this is called GL, general linear n, and usually you put here either R or C, either R or C, real or complex number.
So if there are complex numbers, then the real dimension will be 2n squared.
2n squared, yeah. So either you say, so either it's the n square real dimensions for the real case or n square complex dimensions. So each parameter complex, which means 2n square real. Yeah. Okay. This is because there is no condition. The only condition is inequality, that the determinant is not equal to 0. Is not determinant equal to 1. When if you have 1, then that means an equation is there, right? But here it's just a bound. It's saying that it cannot be 0. That's it. So you have all the n square variable, all the n square. Okay. So this is just the transformation. This is general linear transformation of you choose a basis in n-dimensional space and just making a general linear transformation to a new basis. But this basis better be invertible, and that is the reason for the condition that the inverse exists. Because if it's not invertible, then the basis will not. I mean, it will not span the whole space, right? You want an n basis of n-dimensional vector space to go to another basis. Then the more kind of so essentially, yeah. So this is a big group, but now we start putting conditions on this to get some more requirements on this to get smaller groups. So the first condition is, well, we can say determinant of this m is equal to 1. Okay. This you can think of it. I mean, you can understand it in the following way. That I mean, if I choose, suppose a measure on the space, which is dx1, dx2 up to dxn, the integration measure on this n-dimensional space. Then, if I go to the new coordinates now, dx1 prime, dx2 prime, dxn prime, then there will be a Jacobian, right? The Jacobian will be precisely for this linear transformation. You see, these things do not depend on x. This is just a constant matrices. Okay, that's what I mean by linear transformations. Otherwise, it will be nonlinear transformations. So here, this matrix coefficients of this matrix do not depend on x. So this when you make the transformation from here to there will be a Jacobian involved there. That Jacobian is nothing else but determinant of. If I write x primes equal to mx, or maybe it's inverse. So yeah, this is equal to det m, determinant of m times that. So if you say determinant of m equal to 1, that means this measure doesn't change. So kind of a volume remains the same. So you are changing the coordinates in such a way that you are saying that the volume element remains the same in the new coordinate system. So that is the condition of the. So this, once you impose this condition, then you have SLM, special linear, R or C. I mean, I will not write this all the time. It will be understood that you can choose your field, ring, of whatever you get, whether you choose real or complex, you can choose. The Lie algebra, so this was the finite transformation level. The Lie algebra, the infinitesimal, it will be simply the n square. I mean, you just think of all of these parameters as infinitesimal parameters, so you'll get n square. This Lie algebra will be n squared dimensional. Okay. The dimension of the group is n squared, so Lie algebra must also be n squared dimensional. Yeah? And this one clearly has an ideal, right? Because you have the identity you can put here, right? Identity meaning, so just make the, is that clear? Right? Because it's an arbitrary n square. So the Lie algebra here, Lie algebra is Lie algebra. So maybe I should write GL and N. I will omit this R, GL, N. So this is the Lie algebra. Is n square dimensional again, is n square dimensional, and arbitrary element of this is simply, let's say, let me introduce a notation, Eij. This notation that we will use it later, so I just introduce that here. So Eij is an n by n matrix, whose where all the elements are 0 except the ith row and the jth column. Okay, so this entry is 1. The entry in the ith row and the jth column, and everything else 0. Everything else 0. Okay. So
The basis for.
this is a basis, exactly. This is just a basis for, because any matrix, you see any matrix you can write, so very explicitly it is simply, so Eij is a matrix such that if I look at the Eij with let's say K and L, kth row, and so this is a row, this labels a row and that is a column. If I consider, so this n by n matrix, now what I'm telling you is the components of this n by n matrix. So the kth row and lth column, that component is nothing else but delta ij, delta ik, delta jl. Okay, I mean, it doesn't matter where you put, the position doesn't matter. Okay, so that's the definition of this matrix E. This labeling is just to remind you that the only non-zero entry is the ith row and jth column. This is not the index KL. Right? This is the label for the matrix itself. So therefore, any GLN matrix, say algebra M, I can always write it as some Mij, Eij. These are not numbers. That's a matrix. Mij is nothing else but the element of the ith row and jth column of M. Is that clear? Yeah? To everyone, it's clear? So M, let's suppose M is a matrix. M11, M12, etc. Mn1, etc. So some arbitrary matrix, n by n matrix. Then I can always expand it in this basis. These are matrices. So this is, remember, this n cross n matrices. Unfortunately, this could be a bit confusing because here, please remember that this is not an element of the matrix. This is a matrix itself. This is that n by n matrix. Right? Whereas these are coefficients. These are numbers which are appearing in this matrix, in the original matrix. So this is a number times the n by n matrix, and then you have to sum over all I and j. So that's just a convenient way of writing. I mean, it's clear that any matrix can be expressed like this, right? Any n by n matrix can be written like that. Whether if it's real, then okay, these numbers are real. If it is complex, then these numbers are complex. Any n by n matrix, right? So therefore, I should be able to use the same language to expand, to write for everything else. No? So in particular, for SLN, all we are saying is that I mean, again, I can write SLN matrix, SLN Lie algebra, no? Again, is some n by n matrix, but now what it is, it's traceless, right? It's going to be traceless. Okay? I mean, because determinant is 1. Now, we are saying determinant is equal to 1, and you remember when determinant equal to 1 condition at the level of Lie algebra translates into tracelessness, right? Because when you write this identity plus some small infinitesimal element, identity already has determinant 1, right? So then the rest of the piece will give me a trace condition. So trace of this will be 0. So if there's a matrix M, which is an n cross n matrix, then we have the condition that trace of n equals 0. Then I can choose a basis here where the basis will be simply Eij for I not equal to j, and for the diagonal I can just choose let's say Eii minus 1 over n times okay, you can just write it as, you can just choose Eii where I goes from 1 up to n minus 1, no? Because the last one is automatically fixed, because if I'm looking at the traceless, the trace is 0, so it's automatically fixed. So the last element mnn will be the negative of the sum of the remaining ones. Okay. So it is automatically fixed. So the dimension will be, of course, 1 less. Here dimension will be n square minus 1 because of the determinant condition, which in the language of the Lie algebra, it just means tracelessness. and then the second dimension. One less.
Sir, why traceless? Is it from determinant 1? That's the reason.
Sorry, repeat that again.
Why you say M is traceless?
Like the same thing that we did for SU2 and SU3 and so on.
Just for generator.
Yeah, for generators. Yeah, I'm talking about the Lie algebra now. Sorry, this is the small s. So that was the determinant. Now I talk about the Lie algebra. This is the Lie algebra. Here was the Lie group. This was the SL and R group. Now I'm talking about the algebra. Okay. Yeah. So the level of algebra. Okay, these were the groups. Now these groups, both of these groups are non-compact groups. They're not, for example, let's take SL2 as an example, SL2R. Take the, let's say n equal to 2, please. And look at the SL2R. So it's a matrix A, B, C, D. So 2 by 2 matrix, and the only condition is that AD minus BC equal to 1. No? But that still, even for the real, so you see that this can be, the range is infinite. So this is a non-compact. These are all non-compact. Then we go to the things that which you already seen many times, so I will not repeat them. That's LN. The orthogonal groups, yeah. This do I have to talk about? I think we have done this many times, so maybe I should just ON. Orthogonal groups. So you see, we are just putting more and more conditions. Okay, general linear was everything, was containing everything, but now let's look at the ON group and the SON group, which is nothing else. ON group is those matrices which satisfy the condition that M transpose M is equal to identity. Right? M transpose is the inverse of the M. And at the level of Lie algebra, so this was at the level of group. This is SON is a further condition determinant of M equal to 1. This we have seen before. So this is the level of group. At the level of Lie algebra, this translates into the statement that if I write M is equal to identity plus some epsilon times small m, let's say. Then this condition just tells you that M is antisymmetric. M transpose is equal to minus M. That was the condition here. Okay. The dimension of this group is n times n minus 1 by 2. Again, this we have seen before, which becomes very clear. As we have noticed before, that when you have this nonlinear equation, these are nonlinear equations, counting is a little bit more complicated. But when you have at the level of Lie algebra, these are linear equations. So counting is immediate, right? So this is antisymmetric, so clearly the dimension is n times n minus 1 by 2, right? The most general antisymmetric n by n matrix will have n times n minus 1 by 2. For the SON, again, we have the same condition, M transpose equal to minus M, right? Because this condition is still there. Only on top of it, we have this extra condition, determinant of M. This determinant of M equal to 1 condition will translate into trace of M equal to 0, but that is automatic because if it's an antisymmetric matrix, trace is obviously 0. So this doesn't give any new condition. So this is automatic. Right? So no new condition comes from there. So the dimension is the same. So at the level of Lie algebra, there is no difference between ON and SON. There's no difference at all. And that we saw what is the reason for this, because this equation already implies that determinant of M square equal to 1, right? This equation implies. Because if you take determinant both sides, you get determinant of M transpose times the determinant of M equal to 1. But determinant of M transpose is the same as determinant of M. So you get this. So the only possible values are dit M equal to plus or minus 1. So they are disconnected. I mean, the two components are disconnected. You see? No? So there will be some space where dit equal to plus 1, and there will be another space with dit equal to minus 1. And there is nothing which can connect, right? I mean, you cannot go continuously from a point here to that point, without going out of the orthogonality condition, right? So these are two disconnected components. So identity, suppose you will be in this component. Here you don't have identity. Here you have identity. And when you talk about the Lie algebra, you're looking at the neighborhood, right? So again, let's me again say, for the ON, the group space has two disconnected parts. One part which has determinant plus 1, another part which is determinant minus 1. For SON, we have determinant equal to plus 1, so we have just that part. SON doesn't have this part. SON has this part, and now when you look at the Lie algebra, you're always looking at the neighborhood of the identity. But that is going to be in this part, not there, right? This is not in neighborhood of the identity. So at the level of Lie algebra, there is no difference between SON and SON.
When we exponentiate to find a general root element.
Sorry, repeat that again.
When we will exponentiate the generator to find
Yeah. So you can't find that. You can't get that. You can get this part, but not that. Huh?
It means that for ON you cannot get the whole group from.
That's right. So what do you do? Maybe it was also an exercise problem, right? That a generic element of ON you can obtain as the SON times a parity transformation. A parity transformation will be of this type, right? Because parity will be what? Just you reflect only one direction. So everything plus 1, but say one of them is minus 1. This determinant is minus 1, right? So is the parity. So rotation together with the parity transformation, that is what gives you the ON. So in other words, you take a standard element, I don't know, let's call it, this one is some G, let's say. So an arbitrary element of this can be written as G times an element of this. Well, that's the SO, where is it? Here. So, okay, so that's the orthogonal group. Yeah. I'm going very quickly because I think you've already seen everything, right? The only new thing will be symplectic. So I'll spend a little bit of time there. The symplectic groups. But this we have already seen. So I mean here in the notation I was calling EIJ, I mean this basis. Clearly the basis for this will be EIJ minus EJI, right? So yeah, so because of the M itself, this tells me that MIJ equal to minus MJI. No? So the basis you can use this basis. So this basis. I mean, this matrix will be what? This matrix will be, so this one gives me ith row and jth column is 1. And there, it gives the jth row and ith column. So this is jth row and ith column will be minus 1, right? Because there's a minus sign. That's an antisymmetric matrix. So, right? And so this, you can expand in terms of the antisymmetric matrices. Right. Now let's go to the UN and SUN. Okay. So the UN is again n by n unitary matrices. So you have, let's say, M1, M dagger M is the identity matrix. Right, M dagger is the inverse of this matrix. Of this. So unitary matrices are the n by n matrices which satisfy this condition. M dagger n equal to 1. And so at the level of Lie algebra, you can write M. If I write n is equal to identity plus epsilon some small n, then this basically tells me that M dagger plus M equal to 0. I mean, if you put an I there, then this will become minus. It's a matter of whether choosing Hermitian or anti-Hermitian basis. So maybe I can put here an I there. So then it becomes that. So this means that n is an n by n Hermitian matrices. The Lie algebra is already Hermitian matrices. When you talk about the UN, etc., of course, we are already using complex numbers now, right? Because there's a notion of Hermitian conjugation, so complex conjugation. So we are implicitly thinking of complex numbers. Right? So Hermitian matrices. And SUN, dimensionality of this is n square. This we have counted before, n square real for the UN. Okay. For SUN, we have the further condition, dit of M is 1. And that reduces the dimension by 1, only 1, because a priori you would have thought that this is a complex, the determinant of M is complex number, right? So this should have two equations, right? Because the real part should be equal to 1 and the imaginary part should be 0, so it should be two real equations. But that's not the case, because this already implies that dit M dagger times dit M equal to 1, but dit M dagger is nothing else but dit M complex conjugate. So this equation is dit M mod square equal to 1. So this implies that dit M is a pure phase. So this equation is just an equation on this phase. I mean, for some theta, it's a pure phase. So this equation just sets theta equal to 0. That's all. So actually, it's only one real equation. And therefore, the dimensionality of this is n square minus 1. And at the level of Lie algebra, what it is n cross n traceless Hermitian matrices. Okay, this is all you know. So, okay, now the symplectic. Let me just quickly talk about symplectic. So this, as I said, I mentioned before, symplectic groups. You see that both of these groups, ON and UN, were kind of some symmetries of ON is a symmetry of the n-dimensional Euclidean space, right? Because if you look at the length square, so if I just to remind you, these are all coming naturally as symmetry groups in physics problems, or mathematics problems. So ON or SON were simply saying that if I take the length, suppose I have n-dimensional space, and I define the length square to be this, x1 square, x2 square, up to xn square. So there's some, I have the coordinates x1 up to xn, every point is labeled by the coordinates. So if I define this to be the length square of the vector, okay, then we are asking for the most general transformation, linear transformation, which keeps the length invariant, right? That is what is the ON or SON, right? because you can write this matrix, so I call this matrix as X. Then I can write this length square in the matrix notation as X transpose X. Right? This is a column vector, X transpose is a row vector, and when you multiply the row with the column, you will just get this quantity. And now, when I did the transformation, so what are we looking for? We are looking for a linear transformation such that this quantity remains fixed. Right? A general linear transformation would be X goes to Mx, where M is a matrix. Where this M does not depend on X, it's a constant numbers. So M times X. So if I plug this here, so length square goes to, now we have X transpose M transpose M X, right? You just take the transpose of that, right? And if when we, so if the requirement that this is the same as X transpose X, that's what we are asking for. What kind of transformation I can make so the length square doesn't change, right? This was the old length square. This is the new length square. We are saying the new length square is the same as the old length square. Okay, so that this implies that M transpose M equal to identity matrix, and that is a condition coming for the OM. Now, what about the UN? UN is again you have a concept of, instead of taking real and real dimensional space here, take now and complex dimensional space. I mean complex, so which means the elements are all complex numbers, Z1, Z2 up to Zn. And the length square we define as Z1 mod square plus Z2 mod square and so on, plus Zn mod square.
Okay, thank you. Okay, sorry.
But this again in the matrix notation, if I call this as some capital Z, then I can write this as capital Z dagger capital Z. Right? Now go through the same thing. The most general linear transformation, so I transform by linear transformation, will give me Z will go to MZ, where M is some n by n matrix. Okay, but I want the length to be invariant. Then that tells me the length square will go to Z dagger, M dagger, M Z. Okay, and we want this to be the same length. We don't want the thing to change. Then that gives this condition that M dagger M is identity matrix. So that was the condition. And then okay, the special comes when you say the volume form doesn't change. No? The volume of the element doesn't change, and that gives you a determinant condition. But so what I'm trying to emphasize is that these groups appear very naturally in physics as the invariants of the length square. So of course the length square is this if there's a rotational symmetry, right? If there's not a rotational symmetry, length square will not be that. No, this is for a rotationally symmetric thing, because this tells me that, I mean, whether the vector is here or there, you rotate it doesn't change, right? So the rotational symmetry. Here you have again, I mean, some particular case. I mean, if the length square was not just that, but some complicated function here, it will not be. This will not be the symmetry, right? But for this length square, it is symmetry. Now, so what is a symplectic group? Again, a symplectic group is again coming from some symmetry which you have seen in your Hamiltonian mechanics, no? Because when you go from Lagrangian depends on what? Whatever, L depends on Q dot, right? Q is your configuration, the coordinate, let's say. This could be any dimension. I'm just writing Q, but there could be several Qs, Q1, Q2, Q3, etc. But Q and Q dot, position and the velocities, no? That is what it depends on. But when you go to the Hamiltonian formulation, so H will be a function of Q and P, right? Where basically P is defined as dl, by dq dot. something like that. Yeah. So then you rewrite by Legendre transformation from L to H, right? And then that defines. Now the point is that there is a Poisson bracket between Q and P, which is like QP is equal to 1, right? This Poisson bracket is antisymmetric, so PQ will be -1. Right? This is a Poisson bracket, PB. This is what, when you go to the quantum theory, you replace this by the commutator. You take these guys to be operators now in the quantum theory, and it becomes the commutator. But let's stay with the classical mechanics. You have this 1 and -1. More generally, if I have n dimensions, then Qi, Pj, if this is n dimensional, so there are these I indices. I goes from 1 to n. And here is again Ij. So Qi, Pj will be delta Ij, and Pi, Qj will be minus delta Ij. Right? So now if you put the whole thing as one big column, so one big column, so let's call a column X, which is Q1 up to Qn and P1 up to Pn. Okay. Then you see what you find if I write xi with xj. Now I goes from let me just write like this symbolically. So this could be any of these indices 1 to 2n, right? And this could be any of the indices 1 to 2n, right? Then this is going to give me, as I change all these indices, so let's say let me call it A and B. A and B. Then you find as a matrix A, this will be the element of, it will come like this, identity here and minus identity here. So for example, when A is between 1 and n, then this is Q. Then the only time it will be non-zero is if B is between n plus 1 and 2n, right? Because the n plus 1th row to 2n plus 1, 2nth row. So only in that case, if this is between 1 and n, then that should be between n plus 1 to 2n. So it is this block. And vice versa, when this is P, which means this is between n plus 1 and 2n, then the only time is non-zero is when this is Q, 1 to n, right? So that is this block with a minus sign. Right? So more generally I can write there's some omega AB, this omega AB, where omega is this. So this is very different, you see, from the previous things. Previous things we had the length square was an identity matrix. Identity matrix. Here, actually you can generalize that. You can generalize it to something, anything symmetric matrix. You can do that. But here, on the other hand, it's an antisymmetric matrix. And that makes a big difference. Okay. So now, again, let's do the following. So I want to make some transformation on X, this big X, as some linear transformation, Mx. Okay. And then you find that the requirement that this, what is the canonical transformations? Canonical transformations are the ones, such transformations which do not change the Poisson bracket. Okay. And that basically gives you the condition that M transpose omega M equal to omega. That is the condition. This condition is very similar to the orthogonal condition. Orthogonality condition was M transpose times the identity matrix, because we took the metric to be identity, right? Times M is equal to again identity matrix, right? So this was the metric. And similarly for the SUN, where you have an M dagger identity matrix and was again equal to identity. But here it was dagger because our space was complex. So it was mod square, the Z mod square. No?
And it is also similar to the condition for SO13.
SO1, 3, where you just change the signature. Yeah, exactly. Actually, from the way we are studying, there's no difference between SO1, 3 and SO4, because anyway we are complexifying the Lie algebra when we study the roots.
The SO13 is just non-compact. Right?
Non-compact. So the issue is that, you see, all this analysis, when we go to the roots and so on, we are complexifying the Lie algebra, right, to find the eigenfunctions. But then, so it's the same analysis for all of them. SO1, 3, SO4, everything is the same. But it is then, at the end, you have to go back to impose some reality condition. That's where the differences come. At the level of complex Lie algebra that we have been discussing previously, there's no difference, it's the same thing. But this makes a big difference. The fact that, unlike here, this is symmetric. I mean, this, as I said, I could replace it by some symmetric matrix. And again, I asked this condition. Here again, I could choose some Hermitian matrix. Let's say H. Okay. And then this will be H. The group doesn't change. I mean, the two groups are related by some conjugation. Okay, you can do that. That's not the problem. Of course, the simplest version is just take the identity. Okay. But while this is symmetric or Hermitian, this becomes this anti-symmetric, and that makes a big difference. That's what I'm trying to emphasize. Anti-symmetric. So that's a symplectic group. This group is called symplectic group. The group which is so it's a 2n. So the set of matrices of 2n by 2n matrices is 2n because phase space is double the n plus n, 2n. Phase space is 2n dimensional, and so matrices M which satisfy this condition. This condition.
So, for example, for odd,
odd the phase space is even dimensional. Okay, there's in mathematics. You see, this group is called SP. This group is called symplectic group is labeled by SP. Now there's a distinction. I think physicists tend to use 2n, R, because the phase space is 2n dimensional. But many times in mathematics literature, you will find the mathematicians will write as SPN. Okay. So you have to be careful when you read the literature, any book or something. You should check what do they mean.
The note it is written as
in the notes it's written SPN, is it? Yeah, okay, I think. Because George is more mathematician. The one who wrote
what's the difference?
No, there's just a notation, what you call it. It's the same thing. I mean, what I'm saying is that what physicists usually call SP2NR, mathematicians call it SPNR. So this 2n, when they say 2n, it means really you're talking about 2n by 2n matrices. This n, when the mathematicians use SPN, or also some physicists, I prefer to use this language, this notation, SPNR, because this n turns out to be the rank of the Lie algebra. Rank is the dimension of the Cartan algebra. So to me, this is more convenient. I mean, when I see it, I immediately realize, this is the rank. But okay, it's only reason I'm saying is that when you read some different books, you should check what convention they are using. The conventions could be different. So. Okay, so now again we can count the number of parameters involved. Symplectic group. What is it? Right. So, I mean, if you look at this equation, we want to, again, counting, at the level of infinitesimal, it becomes easier. But if I look at this equation, then you see that this is automatically antisymmetric, right? Because if I take the transpose, m transpose omega n, and I take the transpose of this, you get back m transpose, omega transpose, but omega transpose is minus omega. So it becomes minus omega and n. So this matrix is an antisymmetric matrix. So the total, I mean, this equation will have how many equations? So it's 2n by 2n matrix. So you'll get 2n times 2n minus 1 divided by 2, right? 2n times 2n minus 1 divided by 2. That is the number of equations. This is the number of equations you have, and original matrix itself has 2n. This is a 2n by 2n matrix. So the total number of parameters to begin with were 2n squared parameters, right? So you have so many conditions. So they will fix this many of the coefficients from the total, which was that, and so I have to subtract that 2n times 2n minus 1 by 2. So what happens? What do you get? I can take out a 2n, or 2n I can take out. So you get here 2n minus half of that. So n, am I doing right? 2n minus n, and then plus half, right? Plus half. So which is the same as n times 2n plus 1, right? I mean, I can better to take 2 inside here, because to remove this half. So 4, 2, and 1, right? So n times 2n plus 1. 4n minus 2n is 2n, 2n plus 1. So that is the dimension of this group. Right. So that's the dimension. Now, at the level of Lie algebra, what do we get? So, at the level of Lie algebra, okay, just write m as the identity plus the small fluctuation, and a small infinitesimal element. So, write m as identity plus epsilon x, let's say. Then you get from here identity plus epsilon x transpose times omega times identity plus epsilon x. That's equal to omega. That is the condition we had, right, to the at the infinitesimal version. And now look at the equation, which is just first order in epsilon. Well, these are all plus higher orders. Plus higher orders. Now look at the order epsilon. Order 1, of course, order 0th order in epsilon, of course, is automatically satisfied, right? Because identity omega gives you omega, so that cancels. So at order epsilon, you find x transpose omega plus omega x equal to 0. Right? That is the equation. And if you want, you can simplify. Like, let's call this as y. Okay. Then you see this guy is nothing else but minus y transpose, right? Because if I take the transpose of this, I'll get x transpose omega transpose. But omega transpose is minus omega. No? So this is minus y transpose. So the equation is this plus that equal to 0. So y is a symmetric matrix. Symmetric matrix. Okay. So if you take a completely arbitrary symmetric matrix and multiply by omega inverse, you get x. Huh? So I mean, this is convenient for counting, is what I'm saying. So this is a symmetric matrix. It's a 2n by 2n symmetric matrix. So what's the dimension? How many parameters are there? It is 2n times 2n plus 1 divided by 2, which is exactly that. Okay. So it's the x is. So therefore, this tells you that x is simply omega inverse, but omega inverse is basically the same as okay, omega minus, okay, omega inverse, let me say, times any symmetric matrix. This is any symmetric matrix. That's the Lie algebra. Lie algebra. Yeah, I mean, we will not. This group is non-compact, right? Because already you see let's say if I have, let's take the simple case n equal to 1. So just one Q and one P. Okay. So let's try to see what kind of a group we get. Can I erase this part? I mean, I'm going a bit too fast probably. Okay. But I think you are all. Please stop me if you find any difficulty. Then I slow down. Okay. So let's see. Suppose I look at. So the equation was. So this is the equation. Let's say at the level of Lie algebra, or at the level of group. Let's see what it is. So we have 2 by 2. So n equal to 1. So we have a 2 by 2 matrix. A, B, C. Suppose M is that. And what we're looking at is M transpose, which is A, D, C, B. And then omega, which is 0, 1, minus 1, 0. And then this matrix, A, B, C, D. That's equal to 0, 1, minus 1, 0. Right? This is the condition.
You said that x is equal to omega inverse into y.
That's the Lie algebra level.
But we can easily see that omega inverse is negative omega.
Yeah, omega inverse is negative 1.
So
Yeah,
you
correct.
can write it like that.
Exactly. Yeah. And the negative, I can absorb it inside here. No? Y was an arbitrary symmetric matrix, so I can as well just write like that. Yeah. I mean, so here I can write it as minus y plus y transpose. Yeah. So this we have to. Okay. Let's multiply this out. So you get here minus C multiplying this A minus D and B, and then I multiply this with A, B, C, D. So you get here minus AC plus AC. Of course, this vanishes. Then the non-trivial term comes from here. Minus CB plus AD is equal to 1 from there. And this is going to be automatically antisymmetric, so we can check minus AD plus BC equal to minus 1, and the other thing is 0. So this equation is the same as that equation. I mean, this is just a statement that it was guaranteed to be antisymmetric. So there's only one equation. I mean, this M transpose omega M is going to be antisymmetric. Now 2 by 2 antisymmetric, there will be only one. I mean, this will be automatically, this component will be automatically 0, and that will be antisymmetric. So there's only one equation, which is that equation. But this is the same equation as SL2R, right? If you take suppose that you take this, SL2R was what? SL2R was 2 by 2 matrices with the determinant equal to 1. This is nothing else but the determinant, AD minus BC. Okay. So what we see is that SP. Shall I use this language, because anyway this is what is used in the textbook, in the notes, lecture notes. So I will call it SP1. Okay. So this is SP1. This is what I call SP1. SP1R is the same as SL2R. It's a peculiarity. It just happens for the n equal to 1. This is not happening in the others.
Okay. Can we do symplectic group with complex?
Sorry, repeat that again.
Can we do symplectic group with complex?
Yeah, sure.
If we impose a condition that there is a symplectic group with complex numbers, but it is also unitary, then it will be complex.
Yeah. I was going to come to that. That's why. Yeah. This is So it is not. I mean, okay. This is SL2R, right? This is SL2R, and as we saw before, SL2R is non-compact, right? So symplectic group is basically non-compact, just like SL2R is non-compact. But now what you can do is, so the way to get, so you can get so first you can get a compact version of it. It's a not compact version. But this is not the version that appears in your classical mechanics. Classical mechanics, you're just talking about the phase space, no? In the phase space, when you make this canonical transformation, this M are certainly real, right? Because you have Q and coordinates and the momenta P, these are all real. You're going to make transformations with the real matrix. So in the classical mechanics, this problem is always non-compact version. But you can construct a compact version in the following way. First of all, you complexify. So take all the matrices, complexify M. Of course, it still has to satisfy that condition, M transpose omega M equal to omega. This condition has to be satisfied, but now we let the entries to be complex. So it will be the same dimensionality, which is n times 2n plus 1, but now there will be complex numbers. Okay, this will be complex dimensions. And what you do is you basically take the intersection. I mean, now consider also U2n group. U2n group. U2n is again 2n by 2n matrices, which are now unitary. Okay. So you basically take the intersection between these two groups. So in other words, it should be a symplectic, you are looking at those 2n by 2n matrices M which satisfy this condition with complex entries, which are at the same time also unitary. So of course this will be some smaller thing, right? And that is a compact version. That's compact because U2n is compact. So yeah, many times I think in physics literature you call such a group as USPN. Okay, that's a unitary version of it. In particle physics, if at all, usually it doesn't appear, but if at all somebody would try to use symplectic group as a granification group, then they would use the unitary version. I mean the compact version. Okay, not the real version, which appears in the phase space. So they will use in particle physics. They will use it as in the compact version.
So the compact version is the group with complex entries, or the
with complex entries, but yeah, you take first complexify, okay, and then you take the intersection with another group U2n. This is guaranteed to be compact, and you take the intersection, and that gives you. Anyway, it doesn't really appear in the particle physics so
The
much.
intersection means we impose a unitarity condition.
Yeah, correct. Yeah. So, yeah, as I said, this doesn't really appear so much. But it plays an important role in the complete classification, which is what now we'll be discussing. Okay, maybe I should, because I think from now on I will start discussing the more abstract language because we want to apply to all the Lie algebras, right? So one necessarily then has to use more kind of abstract language. So from now on, I think it will be slightly more abstract. So if there is any thing, you should immediately ask me. Then I'll try to come up with examples. Because when you see examples, it becomes more concrete in the mind. No?
Where are the problems for differentiating? Where are the exercises for differentiating?
Sorry, repeat that again?
Where are the problems for differentiating?
Oh. I didn't, sorry, I didn't do it. Maybe, okay, can I just, I don't know, what shall I, maybe I can tell you tomorrow. Tomorrow I can tell you, right? I didn't have a chance to go through to see what problems you should do. Okay, so tomorrow we'll start talking about the concept of metric. Because so far we said Lie algebra is a vector space, right? Which has an extra structure, commutation relation. Now what we want to do is to introduce some notion of a metric on that space. So that is what is called the Cartan-Killing form. It has some very nice properties, and that plays a very crucial role in the general theory, general structure theory of Lie algebra. So we will discuss that concept. I wanted to do it today, but it took too long.
Can it happen that there is a group which is a non-compact, and that group is a cover or double cover of another group which is compact?
If it's non-compact, then probably it will be infinite cover, right? Probably, yeah.
Because if you, in the symplectic group, if you put n is equal to 2, then the dimension becomes 10, and the dimension becomes 10. And if in SO you put n is equal to 5.
Yeah, so there are some, SO5 is related to USP2, because SO5 is compact. USP2 by some double cover. Yeah.
So it has both the groups have to be the compact for to be double or any finite.
Yeah, correct. Yeah. I mean, going back to this, you said. I mean, let's take a simple example. U1. U1 is just rotation around the circle, right? I mean, rotation on the circle. So which is from 0 to 2 pi. Okay. But I mean, you can think of U1. U1. So if I write, so U1 is acting on a circle. So this is angle theta. So it just changes theta. So any you just multiply by e to the I theta, rotation by theta, right? I mean, so okay. But this I can think of as a translation also, because after all, on the let me call some point x in a interval 0 to 2 pi. Take this interval 0 to 2 pi, and I shift x to x plus theta. Okay, again between theta, but these two are identified. That's what it is, because this angle is going from 0 to 2 pi. So it's like you're identifying these 2 points, right? And then you make a translation. So of course theta is also bounded between 0 and 2 pi. On the other hand, if you look at the real line, in the real line, there is a translation. Translation generates a non-compact group, R. No? Now these two are, so R can be thought of as an infinite cover of that. So infinite time. So you keep going from 0 to 2 pi, or make it 2 pi, again 2 pi, 4 pi, and so on, right? So you just don't identify, you just keep going. So that's a trivial example of a cover, but it's an infinite cover.
Instead of identifying, can you say that x goes to x plus theta mod 2 pi?
Which is the same, right? Which is the same. They say that you are identifying 0 and 2 pi. But in the compact case, I mean, if there are two things are related, then there could be only some finite cover, not infinite cover. So that thing I didn't cover, I think, right? Yeah, there are various kind of accidents that happen, like SP2 is the same as SO5 up to some cover, up to double cover. There are a few such accidents happen.
When we talk about covering, we are talking in terms of Lie algebras, not
the groups. No, the Lie algebra is the same. Lie algebra will be the same.
So we're talking about Lie groups.
Lie groups, yeah.
So if let's say we have a group that is a double cover of another Lie group, so we can say that there exists a homeomorphism between them.
Yes.
So if that's true, so we can't find because compactness is topological invariant.
Yeah.
So we can't find a cover for a non-compact group, a finite cover.
Yeah. That's right. Or it should be infinite cover.
Yeah.
So each point is identified with infinite number of points there. Yeah.
That's finite cover.
That's right. Yeah. Yeah. Okay. So we'll meet tomorrow and then we'll start the formal discussions. Okay.